Welcome to the Problemos channel, season 2, episode 53, the episode which I titled Lanchester Square Law, because in this episode we will solve the problem that is pretty much the embodiment of the Lanchester Square Law. But before we jump into the underlying mathematics, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit for yourself from working with the material that we present on this channel is to go to the homepage of this channel, and at the top of that page in the channel's trailer section find the episode titled The Problemos Channel How To. Watch that episode in its entirety, follow all the instructions that we give in that episode. If you have any questions, by all means, find a convenient place to ask me your question, and I will do my best to find the time to answer your question. But in general, in that episode, we explain and motivate everything that we do on this channel. In this episode, in the context of the mathematical problem S2E53, we will deduce the so-called Lanchester Square Law based on the following input information. Given two armies, the Army A and the Army B, under the condition that initially before the battle the Army A has A0 soldiers and the Army B has B0 soldiers, with the strict inequality between these numbers captured over here, there is strictly more soldiers or fighting units in the Army A than there are soldiers or fighting units in the Army B. We're also told that each such fighting unit in the Army and the Army B possesses the so-called lethal skill captured in the symbols alpha and beta, and by our definition, sometimes this is called firepower. I think it is more appropriate to call these numbers over here lethal skill, because by definition such a skill is translated into the number of the fighting units of the opposing army that one fighting unit of the original army can take out of the fight, out of the battle, per unit of time, before evidently perhaps that unit is taken out of rotation by the opponent army to begin with. For example, the number alpha, the symbol alpha, designates the number of fighting units of the Army B, because for the Army A, the Army B is the opponent. So alpha is the number of fighting units of the Army B. One fighting unit of the Army A can take out of the fight per unit of time, before perhaps that fighting unit of the Army A is itself taken out of the fight by one or more fighting units of the Army B. And likewise, beta is the number of the fighting units of the Army A. One fighting unit of the Army B can take out of the fight per the same unit of time, before perhaps that fighting unit of the Army B is taken out of the fight by one or more fighting units of the Army A. So the same unit of time goes into both numbers, alpha and beta. For example, these numbers could be 0.8, 0.65, or whatever. We hide this information behind the symbols alpha and beta, and we're given the following constraints or the axioms of this particular model of the real life phenomena, which we called a static. We'll understand why there is static battle. There are no reinforcements. Static battle between the armies A and B. The attrition model in this case is linear. The time model is continuous. The ammunition is available in the infinite supply to both armies, and there is no fighting units replenishment, or there is no reinforcement. Once the fighting unit of one army is taken out by the opponent, and what that means, we hide or abstract in taken out, killed, destroyed, blown up, torn into pieces, doesn't really matter. Taken out completely or partially, but taking out means no more danger to the opponent forces for the duration of the battle. And so in this case, no matter how that unit was taken out, no replenishment or no reinforcements are coming, no resupply of the fighting units. In other words, the battle model in this case static in the sense that once the initial numbers are given, that's it. This is all the numbers we have. No new numbers are coming. This is an abstraction. Under these conditions, we're asked two questions. In the first questions, we want to know the number of survivors of the Army A when and if the Army B is totally annihilated and wiped out by the fighting units of the Army B. Let us pretend that the number of the fighting units of the Army A, it so happens, it doesn't matter, the situation is symmetric, so we'll do it for demonstration purposes, and the balance between the lethal skills of both armies is such that the Army A completely annihilates, destroys, and wipes out the Army B. So in the first question, we want to know the number of survivors of the winning Army A when it so happened that no more fighting units of the opponent army of the Army B left standing. That's question number one, number of survivors. The question number two is the annihilation time. We want to know how long will it take the Army A to completely destroy and wipe out the Army B in appropriately chosen units of time. And here again, we see another assumptions. Like I said before, there are way more assumptions. Once you start digging into the question of mathematics goes to war and mathematical models of military encounters, let's say, you will discover there are all sorts of assumptions, all sorts of delicate nuances, offensive firepower, defensive firepower. There are different models in terms of the range in which the fighting units can deliver their munition and so on. We take perhaps the most straightforward toy-ish model of a battle between two armies. And again, there is another assumption over here that, let's say, the battle between the armies A and B has begun. It started unfolding, and at some point, the fighting units of the Army B realized, oh, gee, we're getting wiped out. Well, despite the fact that each and every fighting unit of the Army B understands too well that there is no chance to win. The fate of the Army B is sealed. It's going to be wiped out. They still decide to fight in a business as usual according to these parameters over here. Nothing changes. Everything is static. Toyish in some sense, yes, and we're not debating here the realism, how realistic it is. Perhaps it's not realistic. Many times, for example, the fighting units of the Army B, once they realize they are doomed, they will run away, scatter, give up, surrender, and so on. So this is the mathematical model of the situation when, despite knowing that the bitter end is coming, each and every fighting unit of the losing Army B will be willing and will be fighting till the bitter end until they're completely wiped out. No more fighting units of the Army B left. These two questions should be answered, of course, in a way that in the end, we want to produce two functions, the number of fighting units of the Army A as a function of time, and the number of fighting units of the Army B as the function of time. Again, this is a basically miracle, a toyish situation. Yes, admittedly, in reality, no system of differential equations is solvable analytically. All these systems are solved numerically, but this time it is possible to construct the elementary functions that represent these two functions that we are looking for, which is a finite combination of elementary functions. And this is what we want. In this episode, we want all the details, with no details spared, of how exactly do we start with the axioms of choice, if you will, that lock in our model. And then we produce these two solution functions, these two functions over here, with all the other answers to the remaining questions that follow from this thing. In other words, hand waving or saying, oh, this book says not accepted. Step by step solution, no detail is spared, all the steps are shown in public, all the details are generated by you. So this is the objective, and here is a few words of how does this problem fit into the overall context or fabric of what exactly are we doing with these episodes. In order to make sure that all our viewers are on the same page, and in order to set the 4 episodes that are in progress right now into one context, wrap them into one cohesive fabric. This is what is going on, and this is why we're doing what we're doing. In the previous episode, in season 2, episode 52, we solved 2 problems, the 9-bottle problem and the 9-coin problem, and we showed that even though that, yes, the language of these 2 problems is quite different, but their solutions come tantalizingly close to each other. In fact, very close, maybe even perhaps deceptively close, but under the specified mapping of the local material of one problem into another, these 2 solutions, the solutions of these 2 problems, the geometric and the algebraic, cannot be mapped one into another mechanically. And we saw how, why, and where do these things fail. In this episode, season 2, episode 53, which I titled the Lanchester Square Law, we will solve the problem that is the embodiment of the Lanchester Square Law under the assumptions that I specified, where we assume that the number of the fighting units of the Army A and the mix of the lethal skills of the fighting units of the Army A and B are such that, let's say, the Army A wins and totally destroys and wipes out the Army B. We will solve that problem in this episode. In the next episode, which will be season 2, episode 54, we will solve the problem of a bead sliding without friction along a needle that rotates in the horizontal plane at constant angular velocity, and by doing so it will trace a well-known spiral. That's a beautiful kinematic problem in its own right. But we will solve this problem separately by assuming that this problem knows nothing about the existence of this problem, and in this episode we will solve this problem by assuming we know nothing about this problem over here, and we will spare no details. We will show all the details of how the solutions of these problems unfold. And in the final episode, in season 2, episode 55, the title of this episode will be Mathematical Equivalence, and that is the common thread that runs through all these 4 episodes, the method, the problem-solving approach, to which I refer as mathematical equivalence. We will show that despite the fact that the wordings of these 2 problems have nothing in common, ships of the line, fighting armies, fighting units, ammunition, reinforcement, yada yada, and here is another problem of a bead moving across a rotating needle that spins in the horizontal plane, how this can be different from this, very different. Yet we will show that mathematically the structure of the solutions of these 2 problems is actually one and the same. And in this episode we will show how to, for example, take the solution that we will develop in this episode and mechanically flip it into the answer right away with minimal effort, into the answer to the questions that we will pose in season 2, episode 54, and let us get to it. One way to construct a mathematical model of a real-life phenomenon is to split that construction process into 2 distinct stages. In the first stage, in order to understand how the processes that unfold in a given situation can be described and modeled mathematically, we work under a time model that is discrete. Once we understand how the processes that unfold in a given problem can be described mathematically under a time model that is discrete, we try to switch to a time model that is continuous. And this is exactly what we will do, even though sometimes the so-called recurrence relations that result in the process of modeling a given situation under a time model that is discrete are very interesting, deep, and mathematically hefty in their own right. As such, under a time model that is discrete, we will model time with whole non-negative numbers n, where n varies as 0, 1, 2, 3, 4, 5, and so on. And the smallest incremental chunk of time in this case becomes 1. We will let an, for example, an and bn represent the number of functioning fighting units of the army A and of the army B after n units of time have elapsed. And our definition of a functioning fighting unit of a given army is basically a fighting unit that poses a lethal threat to its opponent. And a fighting unit that is not functioning or that was taken out of the battle, it doesn't have to be physically removed from the battlefield, but it means that it was totally incapacitated, blown up, torn to pieces, burned down, killed, severely wounded, whatever words you think you want to describe this process with. Our taken out of the battle will be an abstraction precisely for that. And with the when we model this combat situation under a time model that is discrete, it is natural to represent that combat or that battle as a exchange of fire or exchange of salvos. For example, the fighting units of the army A reload their weaponry, they aim, they fire. The salvo went out. At the same time, the fighting units of the army B reload their weaponry, they aim, they fire. During this one unit of time, the exchange of fire, the exchange of salvos happen. And what is the result? How we can describe that process, one exchange of fire from either side of the fighting army mathematically? Well, if A, N, and B, N represents the number of still functioning fighting units of the army A and respectively of the army B after N units of time have elapsed, then how can we mathematically describe the number of such still functioning fighting units on either side of the battle after that one unit of time went by and during that one unit of time the exchange of fire happened? Well, we will say that the number of still functioning fighting units of the army A will be A of n plus 1. Remember, 1 is the smallest time increment under the assumption that we work with the time model that is discrete, or we model time with whole non-negative numbers. N plus 1 will be this number, and the number of still functioning fighting units of the army B after n plus 1 units of time have elapsed, and during that one unit of time these two armies exchanged fire or exchanged their salvos. Then how can these numbers be represented? Well, it is natural to represent these two numbers as the difference between the number of functioning fighting units that either army had after n units of time have elapsed, and what? And the amount of losses minus, let's say, L with a sub-index A of n, and here it will be minus L with the sub-index B of n, and basically LA of n and LB of n will represent the losses in this case that were suffered by the army A and the losses that were inflicted onto the army A by the fighting units of the army B after that fire exchange took place. Likewise, L sub B will be the amount of losses that were suffered by the army B and the amount of losses that were inflicted onto the army B by the fighting units of the army A. This is quite natural assumption, and here we need to go back to our initial set of assumptions and recall that what we are modeling over here is a combat that is static or closed in the sense that the initial amount of fighting units, remember initially we had A0 and B0 fighting units before the battle. These numbers are they're fixed, they're static in a sense, and that means that no more new fighting units are added to either army during the battle. These numbers are it. This is what both armies have to work with. That is why in these two relations that we constructed so far, you do not see anything that says plus reinforcements that arrived to the army A and the reinforcements that arrived to the army B somehow. In order to do this, we need to capture this in a way that is mathematically actionable. We need to know something about how this reinforcement is delivered. But according to our assumptions, remember, there are no reinforcements that are available to either army during the battle. That is why we say that this combat model is static or closed, and these are the only terms that we have in our basic relations. And again, the indoctrinated members of our audience know that, of course, we live in a free universe. You're always welcome to ask the following question: are these two relations right or they're wrong? But we know that the answer to that question is meaningless. It doesn't have any sense, because the definition of a model is what? Is a certain set of initial assumptions. If you think that you need to add more assumptions, then by all means go ahead, come up with your assumptions, translate your assumptions into mathematics, but then your assumptions will lead to a mathematical model of a combat that is different from ours. Next, we make two more assumptions for three relevant assumptions in total, as we try to convert the attrition rate into actionable mathematics as follows. We assume that the attrition rate is linear over time, that it is linear with respect to the time during which the attrition took place, and we assume that it is linear proportional to the size of the standing or still functioning, posing lethal threat to the opponent fighting units. We convert these assumptions into actionable mathematics as follows. We spell out the losses function suffered by each army after 1 unit of time during which the exchange of salvos happened as follows. The losses suffered by the army A after and units of time have elapsed and the current salvo exchange happened will be in this time equal. This is we use the precise expression over here, equal to the lethal skill of the fighting units of the army B times this size of the standing units of the army B times the unit of time proportional to the lethal skill, the size of the standing army, and the time. This is the time. Likewise, the losses that were suffered by the army B at the hand of the fighting units of the army A will be what? It will be alpha times the currently sized army A times the unit of time during which the salvo took place. Remember our definition of the lethal skill of each and every fighting unit as the number of the fighting units of the opponent that this one fighting unit of this one army can take out of the battle during 1 unit of time. And of course, units of times are one and the same. Now let's say our functions b of n and a of n are measured in, let's say, fighting units, or if you want, soldiers or people. The symbols b and alpha stand for the lethal skill that is measured in which units of measurement? 1 over time. So we have 1 over time with the time in the denominator. Here 1 represents unit of time. So time in the numerator over time in the denominator cancel each other out in the relation here and the relation here. And what do we have? Fighting units, or let's say soldiers, if you will, on the right hand side of the equal sign, and the losses measured in fighting units, let's say soldiers or people, if you will, or ships of the line. So the dimension wise, the units of measurement wise, our formula makes sense. And again, one more time, I want to underscore two important observations. Number one, I did not make all the necessary assumptions at the beginning of this episode that will lead to this particular mathematical model of combat. We are making these assumptions, adding these assumptions as we move along. And if you think that I missed any other assumptions, then please, by all means, go ahead and put these missing assumptions in the comment section so our community is aware of all of them. And the other thing, it is important to understand here that these are, again, asking whether these are right or wrong doesn't make any sense, because this is our initial assumptions. We say that if the losses are linearly proportional to lethal skill, the size of the standing fighting army, and the time, then the mathematical consequences of these assumptions will be, and we will investigate these assumptions in the next few segments. So these, in some sense, are not the laws of combat that are deduced from somewhere. This is our, we think, reasonable assumption, and the overall goal here is to see what will happen if, just like in theoretical physics, there is no such thing as a law of nature, but there is only a mathematical model of a given natural phenomenon that produces the results that agree with the observation to lesser or to greater degree. And here, again, just like in theoretical physics, these assumptions that we make, the goal of these assumptions is what? Remember, we talked about this very important and fundamental thing in physics in the previous episodes. The goal of these assumptions is to produce an exact solution of an approximate problem. By making these assumptions that we're making so far, we're creating an approximation or an approximate model. But once these approximations are inked, we want to produce a solution of the resultant problem that is mathematically exact. Altogether, after all the assumptions that we discussed about, we will have the following two technically recurrence relations, or a system of two recurrence relations shown over here, where I basically spelled out the losses function explicitly for the army A, and the losses function for explicitly, I spelled out the losses function for the army B, shown here and here. And if we look at these relations that describe this particular model of combat, then we realize there are more hidden assumptions come to life, and we need to make them explicit. First, we see that our relations only account for the offensive firepower, or for the lethal skills that are applied offensively. And that means that we do not really account for any defensive capabilities of either army. Once we realize that that assumption has been made, and we now made it explicit, that means that we are describing a model of a combat that unfolds in the open, where the opponents have a direct view of each other, and they do not have much things to hide behind. There's two more assumptions. We need to make them explicit, and there are a few more. Here we also realize that in a fully escalated mode, we also assume that each and every fighting unit of the losing army, let's say Army B, is willing and will be fighting, even though everyone in the Army B understands that they are facing inevitable destructions. an inevitable destruction. And as another assumption, we also have to make it explicit that each and every fighting unit of the winning army will also be fighting to the very end, even though they understand that they're facing an inevitable victory. And even though here, in some sense, these guys, the winning army, has to continue doing what it's doing in order to win. And one more time, I'm not debating how realistic the realism of these assumptions. We're not debating in this episode. If you want, we can maybe discuss how this can be, of how these equations can be affected by the realism. Maybe we can have a discussion again in the comment section. But how realistic is it that each and every fighting unit of either army has one and the same skill? Well, in real life, this is completely not realistic, exactly, because if we take two distinct people and even if we narrow down the skill to just one highly specialized one-dimensional skill, still in real life it never happens that two distinct people possess one and the same skill with mathematical precision, which is what we require over here, number one. Number two, we say that this lethal skills that possessed by the fighting units of either army, beta and alpha, is constant over time. How realistic is that? Well, that is again completely not realistic, because at the beginning of the battle, when, let's say, humans are rested and they're not hungry, they're ready to go, their effectiveness, their lethal skill will be higher. But after engaging into a grueling combat for, let's say, 7 days, the effectiveness simply cannot be the same realistically, because people will be tired, people will be hungry, they may be wounded, perhaps severely. So there is absolutely no way that that number that we pack into the notion of lethal skill will be one and the same. It will have to vary over time. But again, remember, what we are doing over here is we're creating an approximation of a real life situation, and the end goal of this approximation is an exact solution of an approximate problem. Now that we think that we wrapped our brain around how can this particular model of a military combat translated into actionable mathematics under a time model that is discrete, that is captured by a whole non-negative number n over here, with the smallest unit of time that we use as an increment of 1, we see that in this model of a military combat, we have basically an exchange of, or discrete exchange of salvos. Reload, aim, fire by one army, reload, aim, fire by another army. 1 unit of time goes by, the losses are inflicted and incurred, and now we switch from a time model that is discrete to a time model that is continuous. And what does that mean technically? That instead of reload, aim, fire, reload, aim, fire, and a salvo exchange, what happens now on the continuous model is the two armies fire at each other, more or less, again, as a model, as an approximation, continuously. So what do we do now? Well, n is replaced with our favorite variable t. Now t is modeled with a number that is real, a real number, and real numbers are totally different and very complicated animals. So here it becomes t, everything becomes t. Here everything it becomes t. And what do we do with the smallest unit of smallest increment over the set of whole numbers? Well, 1 becomes delta t. So exactly, instead of 1, we say t plus delta t, a small number that to some extent is arbitrary. That is a small number that is arbitrary, delta t, That is our definition of a time model that is continuous. What type of manipulations we will do here? Well, exactly, we will move a of t to the left-hand side and b of t to the left-hand side of the equal sign. We'll say minus a of t equal minus b of t is equal to, that much should be understood by everyone. Here, move here, from here, move to here, and what is the next maneuver? Exactly, we divide both of these relations through by delta t. To that end, let me erase this guy temporarily. I will recreate it in a second, but here we want to do what? Delta t from here is gone. We divide this by delta t, and we had the similar deal with the mathematics of the population of the army B minus B of t delta t, that is equal to negative alpha times a of t. And what is the next thing that we do traditionally? Exactly, we pass to the limit. We want to pass to the limit in this case when the arbitrarily small amount of time is tended to 0 here, and the arbitrarily small amount of time delta t tends to 0. This mathematics is not really mathematics, this is arithmetic, and we take the same limit over here. Let's be diligent students of mathematics and say what we have to say. Limit when delta t tends to 0 of negative beta times b of t, and the same thing over here. Limit when delta t tends to 0 of negative alpha times a of t. Now we have our actionable mathematics, and what does that mean? What do you guys think? What do these two relations mean? That means that on the left-hand side of these two relations, we have a classical or a textbook definition of the first derivative of the corresponding function over here, the first derivative of the function a of t, and the first derivative of the function b of t. And on the right-hand sides of these two relations, what do we have? We have the limit of a constant, and by the corresponding theorem from real analysis, the limit of a constant is that constant itself, because here on the right hand side of these two relations we have no material that depends on the delta t, on the predicate that we operate on. Delta t tends to 0, no delta t over here. Delta t tends to 0, no delta t over here. And what does that mean? That means that we can collapse all this material, all the hard work that we have done so far, and rewrite our result of actionable mathematics as follows. So for the first equation, we have dA over dt is equal to minus beta times b, and we translate this voluminous expression into a compact way as follows. That means that the first derivative of the function b, which we write as dA dB over dt is equal to minus alpha times a. Now this over here technically is what? Is a system of two ordinary differential equations of order 1, because what we have on the left-hand side of the equal sign is the first derivative of A, the first derivative of B, ordinary differential equations of order 1, and this is a system that must be solved, as some people say, simultaneously. And for the sake of the upcoming computations, I will be often doing what we do in theoretical physics. I will steal the notation from theoretical physics, where we basically put a dot on top of the symbol to designate that this is, usually in physics, many things vary over time. So a dot is the first derivative of this given function over time. Likewise, this will be a first derivative of the function b with a dot on top. That is equal to this expression. The first derivative of a over time is this expression, and this system of linear ordinary differential equations of order 1 is precisely what comes out to be, or what is called, the Lanchester Square Law. And where do these squares come from? The word square, where does it come from? Well, this will become evident in a few seconds next. We're now in the position to answer the very first question posed in this problem and figure out the number of survivors in the case of the fully escalated mode, when one army completely destroys or annihilates the other. And that can be done pretty much instantly by the following maneuver. Remember, these two guys, again, I am partial to physics. This is what we do to physics. This is in my blood, putting dots and using dots. Like 2 dots will be for the second derivative, as we will see in a second, but I will erase this. Remember this notation. Again, notation is just that, notation. You can use any other notation that you like. Parenthesize, primes, it doesn't really matter. So here we do what? We divide the first equation by the second equation. If we do that, what will happen? dt in the denominator of the first equation and dt that will flip into the numerator of the second expression will disappear. So here, instead of dt, we will have db. And here, let's raise it. Well, let's do the right thing. We will have negative beta times b divided by negative alpha times a. That much should be understood. This is a straightforward maneuver. Divide the first equation by the second. This goes into the denominator on the right hand side. This goes into the denominator on the left hand side. dt and dt cancel out. We have eliminated the time variable altogether. At this point, we're time agnostic. And what do we do now? Well, we cross multiply these two ratios. The negative signs cancel each other out. And what do we have in the end? In the end, we will have the following beautiful symmetric expression that looks as follows. Let's put it, let's do it this way. Alpha times a times dA is equal to beta times b times dB. And what do we do now? Exactly, we integrate both sides from a0 to the current value of the standing army A, and we integrate the right hand side from b0 to the current population of the army B. Again, this is a standard maneuver, nothing complicated. We have all the material, we throw it into the mix right away. We don't mess with the constants. Again, I will not be spending any time on explaining how these integrals work. If you do not know what integrals are or how to compute these specific integrals, then it's probably too early for you to deal with these problems. Bookmark this episode, come back to it when you are ready to compute this kind of integrals. I will not spend any time. I will just write down the answer. Constant is carried out from the integral sign. ADA is a squared over 2 plus a constant. Integral of b db is b squared over 2 plus the constant. 2's cancel each other out, evidently. 2's cancel each other out, and we simply write down the result right away. Once you understand what is going on here, this is nothing complicated. What do we have? We have alpha on the left-hand side, and then a squared, the current value of the standing army A, minus a squared 0 is equal to beta b squared minus b squared 0. Again, b squared is the current population of the army B, a square A is the current population of the army A. And this is where the squares came from. Remember, a dA integral of and integral of b dB. This is fundamentally the integral of x dx, and this is what? X squared over 2 plus a constant. This is where the square came from precisely, because we use the definite Riemann integral in this case. We got rid of the constant right away. We wrote the answer, and there you go. Now we obtained the answer that is, or obtained an intermediate result that is completely symmetric. And that means that in this mathematical model, again, it is important to realize that this is not the law of nature. This is not the law of military combat. This is just a consequence, a mathematical consequence of the set of initial assumptions that we made when we went into this problem. And again, the set of initial assumptions or the set of axioms defines the consequence. And we obtained, remember, in theoretical physics and in this problem, the computational goal is what? The computational goal of all this work is to produce an exact solution of an approximate problem. This here is an exact solution. We cut no corners. We took the mathematics head on. The integrals that were here are baby integrals. Overall, this is a small miracle again. And in general, you will see that if you can take any real life situation, and no matter how primitive your model is, you come up with something that makes mathematical sense. That is a big victory. If you can solve the resultant differential equations analytically, this is a total miracle, because in reality, pretty much no system of differential equations that describes this or that real-life phenomenon with reasonable degree of precision is solved analytically. They cannot be solved analytically. The systems are solved numerically. Here we took on the mathematics. We took the mathematics head on. The mathematics was straightforward. This is the result. Lanchester Square Law. This is where the squares come out. And again, based on this mathematical model, there is no a priori or some sort of built-in natural mathematical reasoning for one army to win the other. There is no such reason. If the situation is symmetrical, either army can take over. That means that a more detailed analysis of the prediction of what happens when needs to be undertaken. And again, in a few small number of minutes right now, we will learn that, again, miraculously enough, the explicit functions of a and b of t can be obtained. And we will do that. And that will be a finite combination of elementary functions. That is a small miracle, and you guys can analyze them to death later. But here, what do we see? Let's say temporarily, for demonstration's sake, in the fully escalated mode, the army B completely annihilated the army A. What is the number of survivors of the army B in this case? Well, in order to answer that question, we simply set A to 0 in your mind's eye. Cross this guy. This is 0. The moment you do this, the B here becomes B sub S, the survivors, and we write down the result for the number of survivors right away. The number of survivors in this case, the fully escalated mode, the army B totally annihilated the army A, no fighting units of the army A left. What is the answer here? Well, right away, B squared sub 0 jumps over here, beta taken out from either side, so we have a square root. Again, why is it we take out of two roots, plus or minus, we take the one with the sign plus? Well, because this reflects the number of fighting units, be it ships of the line, tanks, maybe, I don't know, soldiers, whatever it is, it has to be a positive number. So here it will be b squared 0 minus what? Alpha over beta a squared 0. There you have it. This is the number of survivors of the Army B in the full escalated mode when the Army B completely annihilates the Army A. Now, for this number to be real, what has to be? What has to happen? Well, in this case, beta times b squared 0 has to be greater than or equal to, what is this? Alpha times a squared 0 equals, I'm not writing it, but right now we're thinking equals, but again, this number has to be what? It has to be greater than 0, evidently. So the inequality must be strict, and there you go. Again, you guys can analyze it to death. Here, under certain conditions, what we need over here is that the lethal skill figures into the winning situation linearly, beta and alpha, but the population of the fighting units figures into this requirement how? As a square. You see, b squared 0, a squared 0. That is where the square comes into the Lanchester Square Law. Wonderful. Let's go back to our original question. Let's say in the full escalated mode, the Army A completely annihilated the Army B. How do we find the number of survivors of the Army A by the time the Army B is completely annihilated in the total escalated mode? Set this to 0, and the moment you do that, A becomes AS, and then simply solve the resultant equation for A of S. So here we will say that the number of survivors of the Army A, by the time all the fighting units of the Army B have been wiped out, what will it be? Well, it will be alpha A squared minus alpha A 0 squared, flies to the other side, cancel out alpha, so square root of A squared 0 minus, here we will have beta, will couple up, will collide with the b squared 0, so we'll have minus beta over alpha, and then b squared 0. You see, out of 2, the mathematics of this computation says plus minus, but out of 2 roots we take one. Which one? The one with the plus sign, because again, the meaning of our problem is that these numbers have to be strictly positive, greater than 0. Otherwise, what's the meaning of victory when no survivors left? So again, for this number to be real, not to be purely imaginary with the I showing up, what has to happen? Well, in this case, alpha times a squared 0 has to be strictly larger than beta times b squared 0. You see, this is it. Now, before we move on to answering the second question, how long did it take the Army A to completely annihilate the Army B in full escalated mode? In other words, we want to compute the annihilation time as an explicit function here. Make note of this formula over here, guys. I will come back to it. I will not be numbering it, but you guys write down, mark it, give it a number in your records, because in the next episode we will solve the problem of a point mass bead sliding along a needle without friction that rotates in the horizontal plane, and after that we will merge the two solutions together. At that time we will use this formula. One episode from now I will tell you guys, let's come back to the formula that Roman told you about in the previous episode. This is the formula that I will have in mind. Write it down again, give it some numbers so you can easily find it, but in the future episode I will come back to this here formula, and now we will move on to the answering the next question, or the annihilation time of the Army B. In order to answer the second question posed in this problem and recover the explicit shape of the function of the population of the army, let's say A, the winning army, as a function of time, and that will be amazingly enough, again, it's a miraculous case where we can do that. That function will be a finite combination of elementary functions. We need to solve the following linear system of two ordinary differential equations of order 1, as shown over here. Again, I use the theoretical physics notation. Dot designates the first derivative. You can use any notation you like. Single tick or prime, use parenthesized notations, whatever floats your boat, go ahead, do that. I will use the theoretical physics notation. And again, as a word of explanation of what is about to unfold in the next few small number of segments is the following. Yes, as a practicing mathematician or a practicing theoretical physicist, you will never do what I'm about to do in the next small number of segments. But the reason I will be doing what I will be doing is because I want to showcase precisely how the problem-solving approach, to which I refer as mathematical equivalence, work. How does that approach work? And my understanding and my thinking is that you will never understand the real power and the real meaning of that, the essence of that approach, unless you walk the walk. In this particular case, every millimeter of that walk at least once in your lifetime. In other words, that walk that we're about to walk should be walked at least once in your lifetime. After that, you will not be doing it, and you don't have to do it. But once you walk the walk with me, you will understand the power of the theory and what does the theory have to offer. Again, in real life, as a practicing mathematician or practicing theoretical physicist, you will never do what I'm about to do. You will just reduce the given problem to some standard or well-known differential equation or a system of, and use templatized solutions and call it good, move on with your life. The reason I will do and we will do, you will do with me what I am about to do, is to showcase precisely the meaning of the technical essence of the problem-solving approach that I call mathematical equivalence. As such, here, yes, on the one hand, we can stick with the ordinary differential equations of order 1. We can actually borrow the result that we produced in the previous segment, slug it into here. Instead of B, put A, roll through, and stay with the order 1 differential equation. Again, I will not do that for the sake of uniformity of explaining how mathematical equivalence works. I will show you guys how these linear system of two ordinary differential equations of order 1 can always be reduced to a single ordinary differential equation of order 2, not 1, but order 2. And the way we do it is as follows, and that way will dovetail beautifully into our next problem, the sliding bead on a horizontally rotating needle. The way we do here is as follows. Again, this is completely symmetrical. We'll do it with one function and then we'll do it with the other. Differentiate this equation over here with respect to t once, both sides. What will we have? We will have a dot dot equal to negative b times b dot minus b dot times b. Remember, this is a product of two functions, and how do we construct the first derivative of a product? Well, this is a first function times the derivative of the other plus the first derivative of the first function times the other function by itself. But remember, we made all our assumptions, and I probably annoyed the bejesus out of you with all these axioms, this, axioms, that. Beta as a function is not really, well, it's a constant function. It does not depend on time. Consequently, this term will disappear. You see, this term will disappear in this mathematical model. In another model that you are more than welcome to construct, you can perfectly have beta as a lethal scale that is not a constant function of time. Then you will have an extra term. Here we do not have the extra term. But by differentiating both sides of the first equation with respect to time once and observing that beta is a function that is constant over time and its derivative vanishes, what do we have? We have the first derivative of b, and what do? Well, we steal it from here. Remember, this is a system. This system must be solved simultaneously. So whatever material we have across the first equation, we can steal from the second equation, and that's exactly what we do. Instead of b, first derivative of b, we take its right-hand side image, and what do we have? Minus beta times minus alpha a, and what do we have here? Minus and minus cancel out, and what do we have? We have alpha beta a. You see? So far so good. So what do we have? We have the following equation: a dot dot second derivative of a is equal to alpha beta times a. That's it. Single ordinary differential equation of order 2, not 1, but 2. So we eliminate one equation. In this case, we eliminate one equation, but at what cost? At the cost of the increase of the order of the differential equation. That's just 1. Once you understand that maneuver, the next maneuver should be also trivial. We do the same thing over here. Differentiate both sides of this equation with respect to time once. So the first derivative of the first derivative is the second derivative. This is minus alpha times a first derivative. Technically, it should be minus alpha dot times a. You see? In one model, which is perfectly fine, if you're willing to do it, go right ahead, you will have this. But in our model, we agreed that the attrition is not only linear over time, it's constant. The lethal skill possessed by each fighting unit of each army is a function that is constant over time. Its derivative over time is 0, so there is no this term. It's gone. So now once we have a dot, first derivative of a, what do? Because this is a system, we come back to the system, stick our hand in there, look around, yank this guy out, take the right-hand side image of the first derivative of a, put it in here, and what do we have? Minus alpha times minus beta b. Minus 1 times minus 1 becomes positive 1. This becomes alpha beta b. And what do we have again? If we throw the a out, in terms of the material that contains nothing but b, it will be b dot dot equals alpha, beta, and b. You see, so we have this equation. Now look at this equation. Look at this equation. These equations, what they have the same structure. You see, now we're getting close to this perhaps high-flying ideas and some abstract ideas of the structure of a solution of a mathematical problem, because of the corresponding theorems that come from the higher brow theory of differential equations, the theorems that deal with existence and uniqueness of these differential equations are the bread and butter of that layer, and precisely because due to these theorems, we have the fact that the solutions of these differential equations, this one or this one, does exist, and it is unique, it has a well-known shape, and we will establish that shape. Which one of these differential equations you decide to go ahead and solve on your own first is irrelevant. It doesn't really matter for demonstration purposes, because we agreed that just because the army A in the fully escalated mode totally wipes out the army B, we will solve this equation. And I also recommend that you guys remember the shape of that equation, because we will come to a very, very similar, as a matter of fact, fundamentally the same equation in the next problem, in which we will be dealing with a bead sliding over a needle that rotates in the horizontal plane. But again, for demonstration purposes, I will show you guys how to solve this equation with respect to the function a of t first. Here again, as a practicing mathematician or a practicing theoretical physicist, you will never be doing what I'm about to do. You will use the higher layer machinery. In this case, the characteristic equation of this differential equation is trivial. lambda squared minus alpha beta is equal to 0, which means that lambda squared is equal to alpha beta, so alpha 1, 2 is equal to plus minus square root of alpha beta. Then you will slug in these roots into the exponents and move on. But the problem with this is that you guys have to be aware of this higher level of, you have to be aware of this higher level knowledge of mathematics. That's number one. Number two, as a budding student, as a budding mathematician, as a student of mathematics and or theoretical physics, you should be always on the lookout to manifest, showcase your improvisational skill, your ingenuity, your ability to solve problems on your own. And in this particular case, you can do that. You should walk that walk and see exactly what it takes. This is a actually good example of applying of the application of your ingenuity and your improvisational skills. Number two. Number three, the reason I will do what I will do in a few seconds now is to showcase precisely how mathematics works. This will show you what will unfold next is an example of how mathematics evolves, how mathematical thinking, how mathematical ideas evolve. We create or construct any which way, perhaps a highly bespoke solution for this problem. Then we construct a highly bespoke solution for another problem that is similar, and to the third one, and to the fourth one. Then we inhale all four and we say, gee, look at this. If we do this or that, then instead of handcrafting a separate solution for each specific case, we can maybe do a better job and come up with a method that will eat all these differences for lunch and deal with them in a uniform way. And it is possible to solve this equation again in different ways, in many different ways, not just one, two or three different ways, definitely. I will show you the way that requires the least amount of specialized knowledge. So if you're a high school student, then you should be able not only to follow my solution that I will show you, but you should be able to construct that solution yourself. And here's the idea. The main idea with these equations is that these are the equations with the so-called separable variables. And the overall goal is to separate which variables? The function of a by itself on one side and the function and the argument of t, the variable t, on the other side. But that separation of variables is done in two stages. First, we separate the first derivative, a dot, we separate it from the function itself. You see, this is the first separation that we will do, and this is how it's done. Now, also, this lightweight technical ingenuity will be helpful for you in physics. If you come across a similar situation, you can use the same idea. So what is the basic idea? Here, the basic idea is to spell out, on the one hand, the definition of the second derivative. What is the second derivative? The second derivative is the first derivative of the first derivative. So we write dA dot, you see, let's say like this, A dot is equal to dA dot over dt. Do you agree? This is very straightforward, and that is equal to alpha beta A. Now what do? We multiply this equation through by one copy of dt. dt over here cancels out. dA dot dt times dt equals alpha beta A dt. You see, here these things cancel out. And what do we have? We have, as the result, we have dA dot is equal to alpha beta A dt. You see, this is the result that you have. This is a straightforward manipulation, nothing really quite complicated. You don't have to be an Einstein to figure this out. Now what do? Think about it. Put this video on pause, come back when you generated your idea. The winning maneuver here is the following. Multiply both sides of this equation by the first derivative again. You see? So what you will have? Let's write down this on this side. You will have A dot dA dot is equal to alpha beta A dt times A dot. You see, this is straightforward, nothing complicated. But what do you do now? Here you already separated the variables in the first stage. You collected all the material that contains nothing but the first derivative of a on the left-hand side of our equation. And what do you do here? Well, you spell out the first derivative over here again, which is what? Which is alpha beta a dt times dA over dt. You see, it's not complicated. Again, what happens here? dt and dt are gone. What is left over standing? Alpha beta a dA. You see, in a small number of seconds, we separated what? We separated the first derivative of a dA dot, and the function itself, alpha beta a dA. And by doing so, what did we do? Well, we prepared our differential equation for the first round in integration. What we're about to do is integrate both sides of this equation over here. Technically, it will be what? In physics terms, the velocity, and here, generalized velocity, and on the right-hand side, it will be a generalized coordinate. And we will do that in the next segment. In the previous segment, we started with an ordinary differential equation of order 2 shown over here, and through a series of straightforward manipulations, we reduced that equation to the equation shown over here on the bottom, and by so doing, we managed to separate the first derivative of the function a from the function itself over here, shown here and here. And we also noticed that throughout all these manipulations, we have two constant quantities, alpha and beta. The product of two constant quantities is yet another constant, and purely for the sake of brevity, so that I don't have to drag this product around all the time, I will designate this product as follows. Alpha times beta will be omega squared 0. This is a constant, and why I chose a square will become evident in a few seconds. Under this syntactic sugar, if you will, substitution, our original equation becomes a dot equal to omega squared 0 a. This is what you saw at the beginning of the previous segment. This is the equation, and under this substitution, this equation, when we replace the product alpha times beta with the omega 0 squared, what will we have? Essentially the same thing. Let's do this. A dot d a dot is equal to what? Omega squared 0 a d a. Wonderful. What is the next step over here? If you were to solve this problem that way on your own, what would you do? Exactly, we integrate both sides of this equation, and the boundaries of integration in this case are more than straightforward. On the right-hand side, we integrate from A0, which is the initial number of the fighting units in the Army A, and on the upper boundary to the current value, of A. On the left-hand side, we integrate on the upper boundary to the current value of the first derivative of A. In physics terms, this will be our generalized velocity. This is our generalized coordinate. The question is, what will be the lower boundary of integration in this case? Put this video on pause, walk away, think on your own. The correct response here is the following. We go back to our original equation that was the Lanchester Square Law, remember, and we take it from there. It's that straightforward. We take it that a dot at the time t equal to 0 is precisely minus beta times b at the time t equal to 0. And what is that number? This is b0. This is the initial number of the fighting units in the Army B. Consequently, this here expression, negative beta b0, goes where? it goes over here. It is that straightforward. Again, nothing here is complicated. We simply use the material, we use what we have. In other cases, for example, in physics or in other problems in mathematics, this will be 0 quite often, but in this case it's not 0, it's minus beta b0. And again, the integrals over here come out straightforward. Make sure that you guys write this substitution down. We will need it when we'll be doing the reverse substitutions, but it's nothing complicated. It's all straightforward. What do we have with our integrals this time? This time also we have our favorite integral of the shape x dx. The antiderivative in this case is x squared over 2 plus a constant. This is what we have. And once that is understood, then the integration of this material becomes more than straightforward. Let's write it down. What do we have? We have a dot, the first derivative, squared over 2, evaluated between minus beta b0 to the current value of the derivative, and it is equal to omega squared 0, a squared over 2, evaluated from a0 to a. This is it. This is how straightforward that is. 2 in the denominator and 2 in the denominator cancel each other out. We convert this notation into the difference. This is also straightforward. Nothing complicated. This is all middle school level arithmetic at this point. It's not even mathematics. We did mathematics probably a little bit initially when we were constructing our discrete time model, recurrence relations, and translating into the continuous model. Now is just computational calisthenics. So what do we have now? We have a dot squared minus beta squared b0 squared is equal to omega squared 0 a squared minus, I will open up the parentheses on the right hand side, a squared 0. You see, it is that straightforward. So what do we do now? Well, we want to separate the variable called a from the independent variable called t. And where is that variable? It's over here, dA over dt. So what do we do? Constant. What do? We gather all these constants on one and the same side of the equal sign. Exactly. So in your records, you write this. The first derivative squared of a is equal to omega squared 0 a squared plus beta squared b0 squared minus omega squared 0 a0 squared. Again, we simply took this guy and moved them from the left hand side of the equal sign to the right hand side of the equal sign. Omega 0 squared, we want to factor this guy out, so we have one and the same multiplicative constant in both terms. If we do that, that's another middle school maneuver. Nothing complicated over here. This is not mathematics, this is arithmetic. And what do we have here? Beta squared over omega 0 squared b0 squared minus a0 squared. Nothing complicated, middle school arithmetic. Now, in order not to drag this monstrosity around, I will designate it as a k0 squared, another constant. It doesn't really matter. Another syntactic sugar device, if you will. Once we do that, write this down. K0 squared equals to this equation. We will come back to it and we'll unwind it back once we recover the shape of the function a as the finite combination of elementary functions in the argument t. But for now, we simply write it like so. Look at this. So now we have nice and neat k0 squared. Omega 0 squared, omega 0 squared. What happens here? We'll factor it out. Exactly, we factor it out. So now, what do we have? Open paren, a squared plus k squared 0 like that. Now, what do? We take the square root of both sides of this equation. What will we have? Well, here we will have a dot is equal to plus minus square root of this here equation, of this here expression. Across two signs, plus or minus, which one do we pick and why? Put this video on pause, walk away, think on your own. The correct response over here is the following. Across two signs, we pick the one that says minus the negative one. Why? Precisely because if we go back to our generating equations, if you will, what do we see? The first derivative of A, remember, the nature of the process is when two armies fight, the number of fighting units on either side happens what? It does not grow, it doesn't stay the same, it diminishes. And how do we capture that mathematically? One way to capture it is to say that the first derivative of that function must be what? Negative. Beta is a positive quantity. B is a function of the number of units of the army B is a positive quantity. A product of two positive quantities is a positive quantity. Consequently, the first derivative of A is strictly less than 0. You see, so we have to pick over here correctly by the nature of the problem the sign which says minus, the negative sign over here. And now what do? Well, we separate the variables. If we factored out omega 0 squared from the square root, we can carry it out. And what can we say? It will be omega 0 times square root of a squared plus k0 squared. Would you agree? And of course, minus. It has to be the minus sign over here. We simply move out the omega 0 squared from underneath the square root. But this quantity this time, there is no playing around, no choices. This is a product of two positive quantities, so it has to be positive. We take the square root with a positive sign. What do we have on the left-hand side? On the left-hand side, we have dA, we spell it out, dA over dt is equal to this. You see? dA over dt is equal to this. So let's write this down more legibly. Maybe here we have more room. Let's do this. dA over dt is equal to negative sign. So what do we do now? Multiply both sides of this equation by dt. One copy dt, one copy dt. What happens on the left-hand side? Cancel, cancel. And what do we have? Well, let's do it this way. We cancel this, and this is what we have. And what do we see now? Well, in the square root, we have nothing but the material in A. We can move it to the left-hand side and separate the variables. And whatever remains is the material that contains nothing but the independent variable t. Let's write down this result. Divide both sides of this equation by this here square root. What will we have? Well, we will have here the following result, which I will leave for now as it is, because it should be helpful for you guys when you solve problems in theoretical physics or problems in different areas of math. You may come to this point. The boundaries of integration will vary, but fundamentally the result that you obtain should be one and the same. dA divided by square root of a squared plus k0 squared is equal to negative omega 0 dt. And that precisely means that we separated the variables as I promised. We separated A as a function by itself and its independent variable t. And what is the next thing to do? Well, the next thing to do is obviously integrate both sides of this equation according to the appropriate boundaries, because the boundaries in different problems will be different. I will leave you guys with this result. Write it down and remember it, how we got to it. In different problems in theoretical physics and in mathematics, the meaning of this variable, A or maybe T, may be different, but the overall structure of how you get here still will be one and the same. Now that we arrived at a structure of a differential equation that will be the same, amazing enough, across many different problems, and this is what exactly we're trying to experience firsthand in this episode and the next one, we will witness this wonderful miracle. We apply the boundaries of integration to both sides of this equation that are specific to our problem. And in our problem, what do the boundaries of this integration process tell us to be? What should they be? Well, a varies which way. If we integrate this side and we integrate this side, a should vary from a0 because this is the initial number of the fighting units of the army. B, the upper boundary should be a, meaning the current value, whatever it is. And when it comes to the time t, what should be the boundaries be? Well, the lower boundary should be 0 because this is how we start the clock. Two armies lined up and off they go, duking it out from 0 to the current value, t. So this side over here will be quite popular. You will have this result from 0 to t. On the left hand side, you will have to see what your material is. It will vary. And in our case, we integrate from a0 to a. And I still remember all too well back in my time in verbal midterm and final theoretical physics exams, I would attack the integrals that I arrive at on either side one by one. And here we will begin with the integral that you see on the right hand side of the equal sign. It so happens that both integrals in this problem are elementary and they can be dealt with in a straightforward manner. The first one of these integrals is shown over here in front of you. This is a trivial integral in a sense. The constant can be carried out. The integral of dt from 0 to t becomes omega 0 t evaluated from 0 to t, and this is precisely omega 0 t. And what do we have now? Now we go back to our result. In your record, guys, you will have the following result. The integral from 0 to a dA over square root of a squared plus k0 squared is equal to what? Don't forget the minus sign, negative omega 0 t. And we can move on to the evaluation of this here elementary integral that you see on the left hand side of the equal sign. If you know how to evaluate the integral shown over here on the board behind me, then you can safely skip this and a couple next segments over and move on to the point where we recover the analytic shape of the function a of t as a finite combination of elementary functions in the argument of t. But for those who still want to see how this is done, the way we do it is, again, the basic idea here belongs to none other than Leonhard Euler. I, for example, own, I don't remember, 4 or 5, maybe 6 works of Euler, his tomes on the theory of integration and differentiation, algebra, and it is a good idea to read Euler once in a while to begin with. This is never a bad way to spend your time. I also own the works by Newton, Nicomacheus, Euclid, Lagrange, and Lagrange is quite difficult to read, not a single drawing in his work. But anyway, the idea here is the following. We will work with the indefinite integral first. This is simpler. And the idea here that belongs to, again, none other than Leonhard Euler is to go like this. introduce the following substitution: e to the power of x minus e to the power minus x over 2. You see, this is a product. Now, let us evaluate the first differential. dA will be k0 e to the power of x plus e to the power minus x over 2 dx. That much should be understood. This is straightforward computation. We differentiate this and obtain this. And now let us do the following. Let us carry out the following computation. A squared plus k0 squared. You see what the expression that we have in the denominator of the integrand? Let's just run by over here with this substitution over here. So what will we have? K squared 0 in the numerator, e to the power 2x minus 2 plus e to the power minus 2x over 4 plus k0 squared. Again, at this point, it's middle school arithmetic, no mathematics here. The mathematics and the wits, the intellectual voltage was over here to come up with this idea. Why is that? Well, because once we factor out k0 squared, what will we have? k0 squared, and then we will have e to the power of 2x minus 2 plus e to the power negative x plus 4 over 4, negative 2, positive 4 collide, and what happens here? We will have plus 2 over 4, and what is this? Well, this is a perfect square. This comes out to be k0 e to the power of x plus e to the power negative x over 2, and all is caboodle squared. You see, this is Euler's wits in action. When in doubt, read Euler. So now we take the square root of this mess. We get this guy, you see, and this guy goes where? In the denominator. But in the numerator, for the dA, for the first differential, what we will have? Exactly the same thing. And in the first power, modulo the first differential dx. So this divided by exactly this, exactly the same thing, k, so this over square root of a squared plus k0 squared. Small fun, but you guys see what's going on. I basically moved the integrand over here. k0 e to the power of x plus e to the power negative x over 2. Big cancel, big cancel. What remains? Dx. So after this wonderful substitution, what do we have? Dx. And what is this? This is x plus some silly constant. Game over. The integral has been evaluated, and now all we have to do, you see the answer over here is straightforward in terms of new variable, but now we need to unwind the reverse substitution and move x over here and everything else over there. We need to perform the so-called reverse substitution, and this is how we will do it. Here, sometimes when students see this horrible expression or seemingly horrible expression, they think right away, oh my God, what do I do? How do I solve this thing? How do I deal with this beast? Well, the answer is, when in doubt, try to simplify things through a substitution. Of course, introducing a proper or a successful substitution is more of an art than it is science. And again, Leonhard Euler was a absolutely top-notch master constructor and substitutions finder. Here we say this. Let's say we put e to the power of x equals z. Don't worry about what z is. It's just a symbol, one thing. What do we have? Multiplying this thing by 2 and dividing by k0, we have 2a over k0 is equal to what? Z minus, what is this, e to the power minus x? Well, it's 1 over z. You see, multiply this thing through by one copy of z. What do you get? You get z squared, right? Z times z is z squared. Then you get 1 over z times z, 1 minus 1. And then on the left hand side you get what? 2a over k0z. You flip it over, it comes over to the other side of the equal sign with the negative sign. 2a over k0z. And this whole mess is equal to one big fat 0. What do we have now? We have now a good old middle school quadratic equation in z. So usually you see these things right away. You do not need this. You can work with it, but okay, for the benefit of everyone, we work with this. So now we have a quadratic equation. Z squared minus, what is it? 2a over k0 z minus 1 is equal to 0, and the game is over. We're home free. We write down the roots for that equation right away. We know them in our sleep. Z1, 2 is equal to what? A over k0 plus minus square root of what? Let's think about this together. B squared is 4a squared over k0 squared minus ac negative 1 plus 4. 4 over here, 4 on the other side carried out. It's caught over here by divide by 2. And what do we have? A squared over k0 squared plus 1. Game over. How complicated is that? Now, across two roots with the plus sign or negative sign, which one do we pick and why? The correct response over here is we take the root with the plus sign. Why is that? Well, z is e to the power of x. And the graph of e to the power of x looks like this. It never crosses, in some sense, the real axis over here for this graph is what? Is the horizontal asymptote. It never reaches, it never touches 0, it stays over the x-axis at all times. So if you write down it like this, e to the power of x, then it becomes evident that we cannot take minus over here because this here number is always greater than this one, and we cannot subtract. We need to take the root with the plus sign. Once we have that, we have our answer, and then we take the logarithm of both sides, and what do we have? We have x is equal to log. I will use this notation. Mathematicians like this one. This is a natural log. If you do physics, you will do ln. It doesn't matter. The logarithm in base e of what? Of a over k0 plus square root of a squared over k0 squared plus 1, close paren. Game over. Was it complicated? No, it was not. So now let's write the answer. Well, let me keep, to be good citizens of mathematics, we will keep this. And here we will erase this, and we will write down the answer in a more legible form, so you guys have it in your records. So what do we have? We have the logarithm in base e of a over k0 plus square root of a squared over k0 squared plus 1, close paren. And once we throw the boundaries of integration onto these things, what we will have? Well, that answer is quite straightforward. And here I just provided a convenient checkpoint for you guys for the intermediate result. If you were doing this problem on your own, then this is the result you were expected to obtain. Now that we have the antiderivative of our functions, the definite Riemann integral between the boundaries of A0, the initial number of fighting units in the army A, and the current value of the number of the fighting units. of the army A, we have this expression. We evaluated between the boundaries of A0 and A and obtained this expression. Again, this expression over here, again, nothing very complicated. Here we use the property of the natural logarithm of what? Log x minus log y is equal to log of x over y. This is it. From the logarithm evaluated at the upper boundary, we subtract the natural logarithm evaluated at the boundary A0. We multiply everything through by K0, move it in where we have to, cancel things out. This is how the K0 pops out over here. No mystery. This is very straightforward. And now once we have that, we go back to our original differential equation. Remember, we had two integrals on either side. We evaluated the first one, we evaluated the second one, and boom, voila. We have our material, which once we unwind it, we have our function a that shows up here twice. You see, here and here. But now we have our independent variable of t. And now all we have to do is some more middle school arithmetic symbolic shuffling in order to write down the explicit analytic expression for the function a, for a as a function of t, which will be what? Which will be, as we shall see momentarily, a finite combination of elementary functions in t. Once we potentialize the expression that you just saw a few seconds ago at the bottom of the screen, then we will have this expression. Basically, the argument of the natural logarithm will be equal to the e to the power negative omega 0 t. And now all we have to do is unwind the expression for a in terms of t. And the way we do it, again, nothing more than the middle school symbolic shuffling. Multiply both sides of this equation by this horrible animal right here, multiply both sides and get what? Times a0 plus square root of a0 squared plus k0 squared, like so. You see, nothing complicated. What do you see? On the right-hand side, we have absolutely nothing that depends on A. All the A-related material is on the left-hand side of the equation. On the right-hand side of the equation, nothing relates to A. So temporarily, again, pick your favorite symbol. Doesn't really matter. What do you want to call this? Let us call it this time, well, not to mix things up, let's call this uppercase T. Then what do we have? We have a plus square root of a squared plus k0 squared equal to t. Subtract a from both sides. You see, this expression is basically t. Nothing here, nothing, no magic, no mathematics. This is just arithmetic. Now subtract a from both sides. So a from here disappears, minus a. Square both sides. Square this side, square this side. What do you have? Well, let's do this together. We will have a squared plus k0 squared on the left hand side, and that is equal to what? T squared minus 2at plus a squared. This is t minus a squared. Middle school arithmetic. Nothing is going on. A squared cancel out. What survives? Only these guys. So 2at is equal to what? T squared minus k squared 0. Move this guy to the other side. What do we do now? Divide everything by 2t. Divide this by 2t. What do we have? A is equal to what? T squared divided by 2t comes out to t over 2. See, t squared divided by 2t, t over 2, minus, this is minus right here, k squared 0 divided by 2t. You see, This is it. It's fundamentally game over. We have our analytic, amazingly enough, expression in closed form for a as a function of t is a finite combination of elementary functions. So once we understand that, if we write down this guy, as a matter of fact, before I erase the board and take a short break, let us we remember this guy. We will come back to this. We will come back to this expression in the next segment momentarily, but for now, let us just deal with this guy over here. Remember, a squared 0 plus k, let's spell it out. K0 squared is equal to what? A squared 0 plus. Remember the expression that we took. It was syntactic sugar. It was just a substitution. B squared over omega squared 0 b0 squared minus a0 squared. Go back to your records, pull them out. This is what you will see. Big cancel, big cancel. What do we have in the end? In the end, we have beta squared over omega 0 squared b0 squared. You see? And now once we take the square root of all this wonder, square, 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 what do we have? Let's write it down here officially. We will have the following: a squared 0 plus k0 squared will be what? It will be beta over omega 0 and b0. Would you agree? Exactly. Now, for the final step, what is omega 0? Remember, omega 0 is a square root of alpha times beta. Would you agree? Yes, you would agree. So here on the bottom there goes square root of alpha times beta. If we extend the square root upstairs to the second floor, beta over here will be squared. One copy of beta in the numerator will cancel out with this one. And what do we have? Look at this. We have b0 scaled by square root of beta divided by alpha. This is it. It's not that complicated. Now let me take a short break, erase this material now that you guys understand what's going on, but in a few seconds we'll come back to this expression over here. When we divide t by 2 for the first term over here, we will divide this guy. Once we accommodate this, and this over here, we'll simply divide it by 2 and write down already the first term. And then we will attack this guy a few seconds later. Wonderful. From the previous segment, I simply carried out this computation on top. Remember, we had the formula over here for a t over 2 minus k squared 0 over 2t. We did the manipulation over here. We originally had for the t the exponent divided by 2, and then we had this a0 plus square root of a0 squared plus k0 squared, but then we used this expression for k0 squared, collapsed things, translated everything into the original material. So we have beta, alpha, alpha, beta. Here we have the exponent to the negative power, don't forget, over 2. This is important. And the time t over here. Now we just have to spell out this second summoned over here. This is trivial. Remember that I designated k0 squared as a difference of squares, and that difference of squares can be represented which way? Beta over omega 0 b0 minus a times beta over omega 0 b0 plus a 0. You see? Again, if instead of omega 0 we put our expression for square root of alpha times beta, bring up the square root to the second floor, cancel the one copy of beta in the numerator in the denominator, what will we have? Well, let's write it down, save some space for me, guys, so I don't have to take another break. So we go like this. square root of beta over alpha. And here it will be square root of beta over alpha. And now our term k square 0 over 2t will be this expression times this expression. And what do we divide it by? Remember, what did we divide it by? We divided it by this expression. Let's do it this way. It will be, okay, let's write it down. Let me spell it out. It will be b0 square root of beta over alpha minus a0 times b0 square root beta over alpha plus a0, difference of squares, divided by a0 plus b0 square root of beta over alpha times e to the power negative, let's write it down right away, alpha beta times t. What do we see? Big cancel, big cancel. Once we flip this exponent upstairs, what will happen? The sign will become the plus. So this guy comes out here with the sign plus square root of alpha beta t, you see? And what do we have left over here? We have this expression left, but we can carry out minus to be symmetrical out, flips things around. Once we plug in this guy, remember we have minus here, we have minus here. So next, let me take a little bit, take a short break, and I will write down this expression for you guys in one convenient shape that we can reuse later. Here in the middle of the board, I wrote down the expression that is the number of fighting or surviving units of the functioning fighting units of the army A as a function of t, which is a finite combination of elementary functions. This time these functions are exponential, and I put the term that carries the positive power of the exponent e on the left to some tradition, and the term that carries the negative power of the exponent e onto the right. Do pay attention over here. I think I got these things right. Again, all the deductions should be absolutely transparent. For the best results, I recommend that you do all these computations with me, because then and only then, I claim, you will really understand the technical essence of how the method or the problem-solving approach, to which I refer as mathematical equivalence, works. Also, remember in season 1, episode 2, I give you one of several possible definitions of mathematics. What is mathematics? Mathematics is the study of structure divorced from any specific context, and that's exactly what we're witnessing. After the next episode, we will see precisely what that means. So here we have the negative sign. Again, if you guys have any questions, or if I think I made any typos, please keep me honest. I think I did the correct job over here. The minus over here is associated with the positive exponent, and the plus over here is associated with the negative exponent. Over 2 and over 2 here are important. And again, once you wade deep enough into a course on differential equations, all sorts of theory you will study, and most of the books will tell you that the solution of the equation that we just did is a linear combination of hyperbolic cosine and hyperbolic sine. And how do we see that? Well, we glue a0 to the positively signed exponent here, a0 times this, and here's a0 times this. So these two guys can be combined into what? A sub 0 into a with the positive exponent plus a with the negative exponent over 2. This is your favorite trigonometric hyperbolic cosine. And what's the argument? Well, that is the argument. Square root of alpha times beta times t. T is not under the square root. Square root is by itself. Now, if we take This, if we take this sum and glue it to this guy and the same sign to this guy, well, we take minus out, then we have this with the positive sign and this with the negative. That becomes hyperbolic sign. There you go. So minus b0 scaled by the square root of beta over alpha times this. What's the argument of the hyperbolic sign? Square root of alpha times beta times t. T again is not under square root. T is hanging out all by itself. So either one of these functions, I prefer this one. There is less things to deal with, at least in my mind. There's just two explicit functions and the game is over. But now we can do all sorts of things from the theoretical physics perspective. Once we have x of t, our generalized coordinate, we can compute mechanically first derivative of the generalized coordinate is what? Generalized velocity. Once we know that, we compute the second derivative of this generalized coordinate. We get what? Generalized acceleration. So now we have our favorite something x dot equals something multiplied by m on both sides. Mass times acceleration is what? Force. Go back to second law of Newton. So we get our generalized force and so on and so on. We can cast this discussion in the language of physics. But for now, we are done with a of t. And in the next segment, we'll mechanically, again, remember, what did we had originally? A, first derivative of a is equal to negative minus beta times b. So how do we compute b as an explicit function of time t? Well, we compute the first derivative and then multiply that result by what? By the reciprocal of beta. Game over. And that is what we will do next. Now that we obtain the shape of the function a of t, which represents the time evolution of the number of fighting units of the army A, obtaining a similar expression for the function b of t that represents the time evolution of the number of the fighting units of the army B can be done in a number of different ways depending on the target audience and depending on the purpose of that computation. For example, if you are a practicing mathematician or a practicing theoretical physicist, in this situation, most likely you will say the following words. Precisely because the shape, where should I write this? For example, here. Precisely because the shape of the differential equations that we were working with, omega 0 squared times a, represents the second derivative of the function a, and the same thing for the second derivative of the function b, because these two equations have precisely the same shape. Once we obtain the solution of one such equation, we fundamentally and essentially solve the second such equation. As such, in order to obtain the explicit shape of the function b of t, all we have to do is go back to our explicit shape of the function a of t shown over here on top of the board and rename the function a of t into the function b of t shown over here, rename a into b, and then perform exactly two swaps. Swap at the same time two simultaneous swaps. Swap a0 with b0. Swap them like so, as shown over here. For example, b0 went into where a0 used to be, and a0 went where b0 used to be. The same thing over here, this way. And then the second swap is the lethal skills alpha and beta. They must be swapped as well. So over here, for example, we see beta was in the numerator and alpha is in the denominator. And in the final expression for the function b of t, these two lethal skills trade their places. The lethal skill alpha goes into the numerator and the lethal skill beta goes into the denominator everywhere in the second portion over here too. And because unlike quaternions, real numbers always compute under multiplication, the swap of the lethal skills alpha and beta in the product makes no difference. We keep them the same here and the same here. Negative exponent, positive exponent. And voila, we have our expression for the function b of t that represents the time evolution of the number of the fighting units of the army B. That is one way. This is essentially no computations whatsoever, and this result can be written down pretty much instantly. On the other side of this extreme of doing no work is doing a reasonable amount of work, and that comes down to actually solving the second equation. B dot dot is equal to omega 0 squared B. And if you are just starting to learn these things, if this stuff is new to you, then it is actually a good idea to go ahead and solve that equation. Let me write it down one more time. B dot dot is equal to omega 0 squared B. Solve this equation anew, afresh, to make sure that you understood how the idea of separation of variables work and how is it executed. Go through the motions, and here you will observe that at some point, remember, you will reduce this equation to, during the first stage of separating of variables, you will have an equation that looks like this. B dot d b dot is equal to omega 0 squared b db. And how will you integrate it? Remember, the generalized velocity over here, the lower boundary will be what? It will not be minus beta times b0, it will be minus alpha a0. And that is precisely when, where, how, and why alpha, the lethal scale alpha, will crawl into the numerator in this coefficients, and beta will go downstairs. And again, I recommend that you guys do that work and see for yourself, because this is how you develop the understanding of how all this mathematically abstract ideas come about. And the third way of obtaining the explicit shape of the function b of t is shown over here in the middle, and it sits somewhere in the middle between these two extremes. We do not do too much work, but we do some work. And what is the idea over here? The idea over here is to go to one of the two ordinary differential equations of order 1 that make up the Lanchester's Square Law. Remember, we had the expression for the first derivative of the function a as what? Minus beta times b. Remember that? And what does that mean? Well, we compute the first derivative of the function a, which we have explicitly written down over here. This is a mechanical task. For elementary functions, that process can even be automated using the Dijkstra's shunting yard algorithm. There's 0 intellectual voltage here. And then we divide the first derivative of a by what? We take this first derivative of a and we divide it by minus beta, the lethal scale beta. That's it. Game over. We have our function b of t spelled out explicitly as a finite combination of elementary functions. And over here, again, on the one hand, I do not want to insult your intelligence and tell you how to compute the first derivative of the exponential function. On the other hand, it is always a good idea to write things down explicitly at least once in your lifetime and see how these things work. Here we take down the coefficient in front of t, or the variable with respect to which we compute the first derivative, shown over here. This square root of the product alpha and beta comes down here. Here in the second term, it comes down in front of the multiplicative constant with a negative sign, because it is with a negative sign over here. And right now it should be transparent for everyone. If we multiply, or let's say we divide this expression by minus beta, here minus will collide with the minus in front of b0. b0 will percolate over here. When we divide square root of alpha times beta by beta, what will happen? If we lower the square root into the denominator, beta will become beta square. One copy of beta in the denominator and this copy of beta in the numerator will cancel out, and boom, out pops the square root of alpha over beta. And this will go in front of a0 right here with a negative sign. Very transparent. Here in the second term, minus times minus disappears. It becomes the plus. Then the rest of the mechanics applies the same. b0 gets cleared because this coefficient will be multiplied by what? By square root of alpha over beta. This is cleared, and then A0, the initial number of the fighting units of the army B, gets married to square root of alpha over beta. Here the coefficient in front of the time with the negative exponent remains the same as it was. And now we can answer the second question posed in this problem, and that is the annihilation time of one army by the opponent in the fully escalated mode. The task of recovering the time that it takes for the, let's say, army A to annihilate the army B completely is not even mathematics. It is a task that is of middle school variety, the algebra of middle school, nothing else. We did some mathematics initially when we had to construct our model, translate the real life situation into the language of actionable mathematics, and we had to exercise our wits a little bit when we separated the variables in the ordinary differential equation of order 2. After that, it is just smooth sailing, and it's again not mathematics with the capital M. This is just computational calisthenics. Well, maybe evaluating integrals we had to exercise some wits, but here it's middle school algebra and nothing more. So when and if in the fully escalated mode the army A, let's say, totally annihilates the army B, that means that the number of the fighting units of the army B becomes what? It becomes 0. So here we erase B of t, we put 0, over here, we equate this number to 0, and the moment we do that, we qualify the time t over here, not just as a generic time that flows forward, let's say, but the annihilation time, ta and ta. And now the task is go back to middle school, pull out, dust off our algebraic manipulation skills, the basically middle school arithmetic, and solve this equation over here for t of a. This is a trivial task. The way we do it is as follows. We move, let's say, this term to the other side of the equal sign because we have 0 over here. When we do that, what happens to this negative sign? This negative sign gets flipped. So here we will say that this is equal to this. These two expressions become equal. This becomes plus, this becomes minus, and we close the parentheses. So far, so good. Wonderful. Now, what's the next maneuver? The next maneuver is multiply both sides of this expression by, let's say, 2. We clear the 2's. So the 2 is gone here, only exponent left. The 2 is gone here, only the exponent is left. See? Middle school, nothing else. And what is the next step? The next step is to multiply both sides of this equation by a single copy of this exponent. When that happens, this exponent, this power gets the factor of 2 in front of it, 2, and this one disappears. You see, this one disappears. And now what? Now we isolate the exponent. We divide both sides of this equation by this constant over here. So let's write it down here. We go here and we divide this by A0 scaled by square root of alpha over beta minus B0. You see, we can even eliminate the parentheses just to make it look nice. And we erase this constant factor in front of the exponent. Now, what's the next step? Well, the next step is to logarithmicize this equation, both sides of this equation. We apply the logarithm. Obviously, before we do that, we remember that our real logarithm is defined for strictly positive values of its argument. So we will analyze this equation. We will analyze the material after we are done. But once we take the logarithm of this exponent, what happens? The power moves downstairs. The logarithm, the natural logarithm of e is 1. So what do we obtain? We obtain the following expression: 2 times square root of alpha times beta times ta, the annihilation time of the army B, is equal to natural logarithm of this here expression, and voila, we have it. Let's write it down, but before we do that, let us execute the following maneuver. Let us multiply this ratio over here by what? By the square root of beta. Then b0 will be stuck with the factor of square root of beta. Square root of beta in the denominator that is attached to a0 will be gone. Same thing over here. We will glue another copy of square root of beta to b0, and the square root of beta in the denominator here will disappear. Let us perhaps use the red chalk. So the answer for the annihilation time when the army B gets completely wiped out is given by 1 over 2 square roots of alpha times beta times the natural logarithm of what? Let us carefully write it down. We have a0 times square root of alpha plus b0 times square root of beta divided by the symmetrical equation over here, but there is a minus sign here. A0 square root of alpha minus b0 square root of beta. Wonderful. So this is our expression. This is the answer. And I suggest that you guys write down this formula and remember it, because we will come back to it one episode after next during the mechanical translation of the solution of one problem into the other. And I will call your attention to this equation. We will use exactly that one. I will erase now these things at the bottom here. You understand how this equation, very straightforward equation, was solved. There is nothing beyond middle school arithmetic over here. And for the logarithm for this logarithm to be real and well defined, what do we have to have? The argument has to be strictly greater than 0, has to be strictly positive. The numerator is always positive. The only suspicion over here is in the denominator. And what do we have over here? Well, this summand has to be strictly larger than this one. Then this difference will be always strictly positive, and the logarithm will be well defined. If we square these things, what do we have? A squared 0 times alpha must be greater than b0 squared times beta. You see again the squares of the number of the fighting units, or let's say people, soldiers, humans. This is if we take it to be a human combat. Again, shows up and justifies the name Lanchester Square Law. So now, once we understand that, let us do another trivial task. And this time, I will leave this as an exercise to you guys to solve this similar equation. If we go back to, remember we had the expression for a of t. If we equate a of t to 0 and solve the resultant equation for t of a, the annihilation time, but this time when the army B in the fully escalated mode wipes out the army A, what will be the annihilation time in that case? Well, you already know the drill. Use this to test your understanding, but the expression for the time, annihilation time, when the army A gets wiped out will be what? 1 over 2 square root of alpha times beta This is evident as it is, and then again we will have the natural logarithm, and what will be here? Well, again, here in this case, because what do we have? We have no time involved. We just have to swap again A0 and B0 and alpha and beta. So the correct answer is the following: B0 times square root of beta plus A0 square root of alpha divided by B0 times square root of beta minus A0 square root of alpha. This is the expression that you will obtain when you solve the equation A of t is equal to 0. Again, this is straightforward arithmetic, middle school, nothing more. This time, however, look at this. For the logarithm to be real and well defined, what has to happen? This summand has to be strictly larger than this one. And if we square both sides, what will we have? We will have the following requirements. B0 squared times beta has to be larger than A0 squared times, sorry, not the square root, times alpha. This is a requirement again. Look at this. In the case of complete victory in the fully escalated mode, the lethal skills figure into the condition here in the first powers. So this is the linear dependency, so to speak. But the number of fighting units figures into this condition. In what? In the squared, as the squares, B0 squared and A0 squared. Again, one more time, the solution, the integration, this is the relic of the past, so to speak. People say when they integrate a differential equation, they actually solve it. But the equation that we solved, it essentially had the following form. Again, borrowing everything from the theoretical physics world, our equation looked like this, where Q is a generalized coordinate. We saw how to solve this equation using the least amount of specialized knowledge. You do not need to know what the characteristic equation is, how to construct the answers, linear combination, this and that. All we did over here is we exercised our wits in order to separate the variables and come down to the functions that could be integrated amazingly and miraculously enough in the elementary way. And again, this way that I showed you guys is just one way. There are other ways to solve this equation, but the way that I showed you requires the least amount of specialized knowledge. Now that we are done with the problem S2E53 completely, we obtained all the results that we were looking for. You guys can analyze these equations. What happens if, for example, let's see, the different cases to analyze. You want to juxtapose A0 against B0 to see is A0 is greater than B0, equal to or less than, and then you want to juxtapose alpha against beta. Again, alpha is strictly less than beta, equal to or greater than. What will happen? Now you have all the answers. You have the explicit functions for the populations of the fighting units of both armies, A and B, as the function of time, and you have the answers for the annihilation times. What happens? You can carry it out on your own, and meanwhile we will move on to a new challenge next. Our next challenge will be the second problem in physics for the season number 2, that is S2P2. Remember that with the letter P, we designate the problems in physics, and amazingly enough, I think that I remember pretty well that this problem was one of the problems on one of my verbal theoretical physics exams back in the time. In this problem, we're told that in the horizontal plane, we pay attention here, in the horizontal plane, we have a thin needle, let's say, or a rod, massless rod of length L. That length is given, rotating in the horizontal plane with a constant angular velocity omega 0. Omega 0 is given. In other words, horizontal plane, massless rod, rotating at constant angular velocity with respect to or about certain fixed axis of rotation. For example, over here, somehow things are fixed. We do not know, we do not care. So this rotation is happening, and with L0 units of distance, which is obviously less than L, shown over here at that distance from the axis of rotation, on that rod, on the massless rod, there sits a point mass, let's say a bead, that is fixed to, let's say, axis of rotation with a thread, let's say. And that system rotates in the horizontal plane with the constant angular velocity. This is the steady state. The rod rotates in the horizontal plane with the point mass attached to the axis of rotation at the distance L0. This distance is fixed. The whole thing is in the steady state. Then at some point, the thread or the little rope, the thread that keeps the bead, the point mass at the fixed distance L0 from the axis of rotation, is cut. And then what happens? Then this point mass, the bead, starts sliding without friction towards the other extremity, towards the free extremity of the rotating rod. Zzz, and off it goes. There is no obstructions or anything. There are two questions in this problem. We're asked to find the separation velocity of the bead with respect to the rod. Right now, with respect to the rod in the steady state, when the point mass is fixed at the distance L0 from the axis of rotation with a thread, what is the velocity of the point mass with respect to the needle or with respect to the rod? 0, exactly. But once the thread is cut and the bead begins sliding without friction along the rod, its velocity begins to grow. So by the time the bead jumps off this rod, we're asked to recover the separation velocity of the bead with respect to the rod. That's number one. Number two, we're asked to compute the separation time. The separation time, or the time that it takes the bead to start traveling from the distance L0 from the axis of rotation, cover that distance, and jump off that rod. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will present my solution of the physics problem S2P2.